equation. So here I'm going from 2 plus to 0 in terms of my oxidation number. And so this is a gain of electrons. And when we gain electrons, that is reduction. Then for my aluminum, I'm going from 0 to 3 plus. So that is a loss of electrons, which is oxidation. So I'm expecting to see that verified for the cadmium and aluminum when I look at those values over here in the reduction potential table. So for cadmium, cadmium is negative 0.40 volts, standard reduction potential, and then the aluminum is negative 1.66 volts. And we're always expecting the value that is the highest, so the most positive, or the least negative, right, to be reduced. So that is my cadmium, and when I look, that is what I identified from the equation as well. So when I'm calculating my E naught of the cell, I'm going to do the cathode minus the anode. So my cathode, the cathode is reduction, and the anode is oxidation, anox, red cat. So my cathode is negative 0.40 volts minus 1.66 volts, and this is negative, right? So that ends up being a positive overall. And when I add them together, I get 1.26 volts. Okay. Notice that even when I look at these reduction potentials, when I notice that like my aluminum is oxidation and my aluminum doesn't match this equation, right? Because it's going the other way. When I plug it into the equation, I'm not changing the value for this E under standard conditions for that. I'm always leaving it as a reduction. So even though I'm changing the equation, when I'm dealing with the calculations, I do not ever modify that number. Now you could, there are different schools of thoughts about how to think about oxidation and reduction and adding those ideas together, but I like to do it the same, no matter if it's voltaic or electrolytic, and this allows me to be successful in both areas. How many moles of electrons are transferred? Well, we have a 2 plus and a 3 plus. And we know that 3 and 2 meet happily at 6. So if we were to balance those half reactions, we would find that each of them has 6 moles of electrons that are being transferred. And that is what's giving us that energy, that electricity that we're being able to harness in our galvanic cell. Calculate the value for delta G0, delta G naught in kilojoules. So I do have to know, this is on my equation sheet, and that is equal to negative NF E under standard conditions. So that is equal to negative, we said 6 moles of electrons. And then we have Faraday's constant, 96,485 joules per volt moles of electrons. And then I'm going to get rid of this because we don't need that anymore. And then the last term is the Ecell, which we already got in our part A, so 1.26 volts. When I look at what's going to cancel, my moles of electrons cancels, my volts cancels, and I'm going to be in joules per mole of the reaction, essentially. It does want kilojoules, though, so I will have to do a conversion at the end. So I get negative 7.30 times 10 to the 5th joules. And when I divide by 1,000, I get negative 7.30 times 10 to the 2nd kilojoules. Is this thermodynamically favored? Well, that means that our Gibbs free energy is negative. That's how we know that. And so I would say yes, because we have a negative delta G value. All right, the last part of this question is about electroplating. So if I use this setup to do that electroplating, how long in minutes would it take to completely consume an electrode composed of 2.50 grams of magnesium if the current is 0.750 amps? So first I need to know like how many moles this is, because then I could figure out how many moles of electrons are generated in this reaction, and then relate that to the coulombs in Faraday's law per moles of that electron. So 2.50 grams of magnesium. I know that for every 1 mole of magnesium, it is 24.31 grams. Okay. Then I know that for every 1 mole of magnesium, I will produce 2 moles of electrons because they form a +2 ion. So now I'm in moles of electrons. Now I'm using Faraday's constant. I know that for every 1 mole of electrons, I will produce 96,485 coulombs, which is a value of 19,852.88 coulombs. Then I'm going to use the amp value that I know. So 0.750 amps is equal to 19,852.88 coulombs per time. And it's really coulombs per second, right? So when I solve this, I get a time of 26,500 seconds. But this problem actually wanted minutes. So I divide by 60 seconds because there's 60 seconds in a minute, and I get 441 minutes. So it takes 441 minutes to completely consume 2.50 grams of magnesium.